So let's imagine a situation where we have a piece of material. This will be our coordinate direction, x. The material is going to be insulated on the top and the bottom. On the left side, we're going to hold that hot. On the right side, we're going to hold it cold. So therefore, heat flow is going to go from left to right. And it's a vector, so it's going to be pointing from left to right. Remember, it has magnitude and direction, but in this case, it's just one-dimensional, so it just points from left to right. The temperature of the object is going to be a field, so it's going to depend upon x and t. So we want to describe the heat flow and the temperature of this object as, say, for example, we increase the temperature on the left or something along those lines. So what we need to do is we need to draw a little box. This will be what we call our control volume. So we'll just arbitrarily define this point as x equals to 0, and we'll define the length of this to be length L, and the height to be h. And what we're going to do is we're going to assume that everything is only changing in the x direction, so temperature does not vary across this thickness due to the insulation. And also the heat flow just flows from left to right, so there's no heat flow going up out into these boundaries. It's just going from left to right. So everything only depends upon the dimension x. So when we write our conservation of energy for this box, we're going to say the time rate of change of the energy stored is equal to the heat in minus the heat out. We're going to have to figure out what each of these terms are in our equation. So let's start with the time rate of change of the energy stored inside our box. So remember, we're talking about the thermal energy stored inside this control volume. So now you might remember an equation from physics that looks something like this. It says the change in the thermal energy stored. Maybe in physics it's possible. You use the variable Q here, is equal to m, the mass, C, the heat capacity or specific heat, times the change in the temperature. Now it's important to remember this change or this delta that we include here, because energy is something that we have to talk about a change relative, and often the reference is irrelevant or doesn't matter or is arbitrary. So an example of this might be potential energy. So imagine if I had an object with mass m, acceleration due to gravity, off the ground by a height h, we would say that the potential energy is equal to mgh. And now you probably remember from mechanics that this, what we call h is equal to 0, actually doesn't matter. I could also likewise say, let's define a point down here to be h equals to 0. Forget that. Let's go all the way down to sea level. I haven't actually changed the problem. I've changed what you might say is the potential energy because h has changed. But in working any problem, it's only the change in the potential energy that matters. So the reference, what I call h equals to 0, is irrelevant. So likewise in thermal energy or in all problems with energy, there always has to be a change from some state or a change from some reference. So we always have to write a delta in the energy stored. Okay, so now that we got that out of the way, let's go to our formula. The change in the energy stored is equal to mc delta t. Now our object is one where temperature is a field variable. Temperature depends upon x and t. So what's the temperature we use in our delta t for our formula? Well, what we have to do is now have to remember it's a field variable, so we have to integrate with respect to space. So what we'll do is we'll say that the amount of energy inside our box is the integral. We'll integrate from x equals to 0 to L of the mass density, rho, mass per unit volume, times the specific heat or the heat capacity, which is a property of the material, times the temperature, which is a function of x and t, so time and space, minus some constant that I'll just call Tref, some arbitrary reference that we're going to measure temperature relative to. And again, I'm integrating that with respect to dx. And if you go back to our drawing, the material also had thickness h, so I need to multiply by its thickness to get the total energy inside that box. So that's our change in energy stored. And the change is the change in energy when the whole object is at the reference temperature T ref. Now in our equation, our balance of energy, we had the time rate of change of the energy stored. So I'm going to introduce the time rate of change of our integral. Now, our region of integration that we're integrating from x equals to 0 to L is held fixed with respect to time. So therefore, my order of operations doesn't matter. I can switch the order of differentiation or integration. So I can move the ddt inside my integral. Likewise, I'm going to assume that my material constants, the mass density and the specific heat, are just constants and they don't change with space or with time. So I can pop them right outside my integral with no trouble. So I have the thickness times the density times the heat capacity. Now let's move my derivative inside there. Now you might notice a subtle change here. I switched my ddt to this funny looking symbol, which is the partial derivative with respect to t. That's just a sort of a notation, right? Because here, when we integrate the temperature, which is a field, over a domain x, the integral is only a function of time. So the integral with respect to x is only a function of a single variable, t. So it's proper to use the ordinary derivative, ddt. Here I'm taking the time derivative of a variable which depends upon x and t, so I should be using the partial derivative. Now the final thing in our little equation here is, if you note, I'm taking the partial derivative with respect to t of my temperature field minus my reference temperature, but that's just a constant, so its change with respect to time is 0, so I can essentially remove it. And now I just have the partial derivative with respect to time of my temperature field integrated over my domain from 0 to L. Now up here I was careful and always noting that I have a function of two variables. Here for compactness I've just dropped that notation. So you have to be a little bit comfortable with writing things out explicitly, but after you get kind of experience, you get annoyed by writing all these parentheses with x and t, so it's okay to drop things. But you always have to remember in your mind, if you do that, that in fact it is a function of x and t. Now let's go back to our sketch. So we've written out a formula for this guy here, the time rate of change of the energy stored. Now we have to figure out what's the heat in and what's the heat out. So if we go to our control volume here, the heat in is simply the heat flow that's coming in along this boundary here on the left at x equals 0, because remember we've defined heat flow to point from left to right. So that's positive heat flow, so that's heat coming into the box. Over here at x equals to L, we have the heat flow coming out of the box. So the heat in and the heat out is nothing more than this heat flow variable that we've defined, Q, on the left and the right. So the heat in is nothing more than the heat flow which defined at a point, x equals to 0, the left boundary of our domain, which can change with time, times the thickness of the material, h. Right, we don't have to worry about integrating with respect to y or the height of the material, right, because q only depends upon x, so it's constant, so we'll just multiply it by h. The heat out, only now we need to define it at a point, x equals to L, on the right boundary. So the heat in and the heat out is nothing more than the heat flow on the left and the right of the domain. So if we put all this together, we have the time rate of change of the energy stored in minus the heat out. You'll notice this equation has an h on both sides. So I can cancel out the thickness of the material, which makes sense because this is a one-dimensional problem, so that makes sense that should drop out of the problem. And now let's do one more change to this, which might seem a little bit weird at first, but in a minute you'll understand why I do this. I'll leave the term on the left alone, but I'm going to rewrite the term on the right using the fundamental theorem of calculus, which is nothing more than the definition of the derivative. If I take the integral of the derivative of a function, I just get the function evaluated at the 2 points. That's simply the definition of the derivative in what's called the fundamental theorem of calculus. I have to be a little bit careful here because here at x equals to 0 it's positive, and at x equals to L, it's negative. So I need to pop a negative sign in there to make that consistent. And so I've just redefined this function evaluated at 2 points as the integral of the derivative using the fundamental theorem of calculus. Seems like an odd thing to do, but let me show you why I do that. I can group those terms together, and I can group them together inside the integral. So now I have everything inside the integral integrated over x from 0 to L equaling to 0. So now let's think about what this means. So I have the integral of something which is equal to 0. So if I integrate anything and it's equal to 0, there's only 2 options. Option 1, the thing that I'm integrating is 0. The integral of 0 is 0. So I could have the option that the thing that I'm integrating, is equal to 0. The other option is I could have the case when I integrate something like sine over 1 period. Here I've got some positive area and some negative area, and therefore they cancel each other out. So it's a little positive here, it's a little negative here, and the result is that the area under the curve is 0. However, when we derived our equation up here, this domain 0 to L in a sense was arbitrary. If we go back to our derivation, nothing would change if I define that to be half the domain. So now I'm integrating from 0 to L over 2. So if we go to these 2 cases, well, if I integrate something which is identically equal to 0 everywhere over any arbitrary domain, be it L, L over 2, or L over 4, the expression here that something is equal to 0 still holds true. However, if I integrate sine over half of the period, so from 0 to L over 2, say, I get a positive number, so that is no longer true. So our only option then is that something is equal to 0 everywhere. In this case, something is this expression here. So that gives us a equation which has to be true at every single point in the domain. So this expression here, which relates the temperature field, which is a function of x and t, is related to the heat flux field, which is also a function of x and t. And it tells me that the rate of change of the temperature with respect to time is related to the heat flux, the derivative of the heat flux field with respect to x. So this is great, except there's only one problem. We have one equation and 2 unknowns. We're trying to solve for the unknown temperature and the unknown heat flux field. So we need some relation between those 2, which at this time we don't have. Okay, so now we need a way to relate the temperature to the heat flow so that we can finally solve for something. So the way we have to use this is use a constitutive law. A constitutive law isn't a law of nature. It's not something like a conservation of energy that has to be true, but it's something that we observe to be true. It's kind of an empirical law. It's a law of a particular material. There's no real fundamental way they can be derived, but they're sort of empirical laws that we observe to be true for certain materials. In heat flow, the empirical law that we use is something called Fourier's law. This is the same Fourier, if you've ever heard of Fourier series. He was a famous guy back in the 1800s. He was a French scientist who was actually advisor to Napoleon, so kind of that era. And what his empirical law says is that the heat flow vector, Q, is related to some property of the material K. This is something that we call the thermal conductivity. You probably have some notion of thermal conductivity already. You know that certain things conduct heat better than others. If I gave you a pot of boiling water and I gave you a wooden spoon and a copper spoon and I told you had to hold one with your hand and dip it in the water and hold on for a minute, you would probably pick doing that with the wooden spoon and not the copper spoon. If you made that choice, then you know Fourier's law and you know thermal conductivity. But again, this is an empirical law that relates heat flow to gradients in the temperature field. So if we have a temperature field, T, which goes from hot to cold and looks something like that, this law tells us that the heat flow is going in that direction, and it tells us that the magnitude of the heat flow is proportional to the temperature gradient. So if I had a shallower temperature field, then the heat flow would be teeny tiny, and if I had a steeper temperature field, the heat flow would be greater. Again, this is an empirical law, need not be true, but for many, many, many materials, it turns out to be very close to being true as far as the best experiments can tell. So we're just going to simply substitute this empirical law or constitutive law into our equation. So we'll simply substitute in Fourier's law for Q. So remember, Fourier's law is simply related those two terms of our equation. The thermal conductivity K is often a constant for many materials. It's a constant that we can look up in a book or look up on Wikipedia. So if it is in fact a constant, I can pull it outside of that integral. And I'm left with an equation that looks like this, which is now only in terms of our unknown temperature field. It relates the derivative of the temperature with respect to time to the second derivative of the temperature with respect to space. We have three material constants, the density, the specific heat, and the thermal conductivity. If those are in fact constants, you can see that we can group them all together, and it's a grouping that shows up so often that we often give it a new name. This thing here gets a new symbol. It gets the symbol alpha, and it's called the thermal diffusivity. And if we think about the units of this thing, on the left side we have temperature divided by time. On the right side we have temperature divided by something that has units of length squared. Remember, derivative operators have units. So it's 1 over length squared. 1 over time are our two derivative operators. So what does that mean the units of alpha have to be? And our parameter of the thermal diffusivity has units of length squared over time. Okay, so now we're left with our equation. We call it the heat equation. In order to solve this equation, we're going to need three things. We need initial conditions and two boundary conditions. So we'll talk more about this in a later video. But the way you know what you need is just by counting the order of the derivatives. So I have a first derivative with respect to time, which always means I need one initial condition. And I have two derivatives with respect to space, which mean I need two boundary conditions. So these make sense because the domain only extends from one point to another. So we have to know how the domain is coupled to the universe around it. And since we're talking, this equation is only describing the change of the first derivative, we have to know where the system started. So we also have to know where we start and how the domain is connected to the universe around it. But we'll save that for another video. Let's talk a little about physically about what this equation might mean. It's relating the first derivative in time to the second derivative in space. If you remember from math, the second derivative we always connect to the curvature. Curvature of a function. So let's talk about what that means. So we're relating the time derivative to the curvature in space of the temperature field. Let's imagine at time equals to 0 I have a temperature field that looks like this. And let's think about what happens to this point right here at this particular location in X. Here the curvature is what? Upward or downward? Well, it's pretty obvious. It's curvature downward, so it's a negative number. So here the curvature is negative. So that would mean that with respect to time, if this is a negative number, the temperature is decreasing. That point is cooling. And that makes sense physically, right? Because you've got a hot thing surrounded by cold stuff. So it makes sense that with time, that point is going to cool off and it's going to decrease with time. If we change the argument around and said, okay, well, what about this case? We have the curvature upward. Well, it's pretty obvious now that this point is going to increase in temperature with respect to time because this point has positive curvature, but it's got hot neighbors and it's kind of cold, so the neighbors are going to pull it up and it's going to increase with time. So that gives us some intuition about what this equation means. There's one important one that you need to think about though, which is what happens when the temperature is linear. A line has no second derivative. Its second derivative is identically 0. So that means if we look at a point here, or anywhere along this line, when we have a linear temperature field, the curvature is 0. So therefore, that means that if the curvature is 0, that the time derivative is 0, so this point isn't changing. It's perfectly happy just staying at that point in a steady state. And that makes sense because this point is at some temperature, its neighbors over here are hotter, its neighbors over here are colder, so it's kind of being pulled down cold by this guy, but being pulled up hot by this guy, and they basically balance out and everybody's happy being in equilibrium. So for the heat equation, when things come to equilibrium, at equilibrium, when the time derivatives are equal to 0, then the temperature field is linear. It could also be a constant, because a constant is a line, just to maybe a simpler one, so it can be constant or linear at equilibrium.